Hello, and welcome to our video on antiderivatives and more advanced complex topology. Let's start with a function f that's defined on some subset D of the complex plane. We say that an antiderivative of f on this set D is a holomorphic function big F defined on D such that big F prime of z equals little f of z for all z in the set D. So this is exactly the same definition as we would have for an antiderivative in real-valued calculus. And let's remember how we can construct antiderivatives in real variable calculus. If you have a function f defined on a closed bounded interval a to b in the reals that's continuous, the function f may take complex values, but it's a function of a real variable. Then you put big F of x equal to the integral from a to x of little f, and that's an antiderivative of little f. This function, big F defined here in star by the integral, well, the integral exists because f is continuous and therefore f has to be integrable, and then the fundamental theorem of calculus tells you how to differentiate big F. So the natural question is, can we adapt this definition to produce an antiderivative of f defined on a subset D of the complex plane? Well, we know how to work with integrals now of functions defined on subsets of C. So what would be the analogs of this sort of base point a and x in the integral star? Well, we could fix a point z0 in D as the base, and then the idea would be that we'd integrate over the line segment from z0 to a point z and call that the antiderivative. I mean, that's basically what you're doing in star. You're integrating from a to x, that's integrating over a line segment. So we define big F of z to be the integral over the line segment from z0 to z of f. And in my notation, when I write this integral over the line segment from z0 to z, I'm really meaning the integral from 0 to 1 of f of 1 minus t times z0 plus t times z minus z0 with respect to t. That's the parametrization of the line segment from z0 to z that we always use. So this big F seems like a good candidate for an antiderivative of little f. Let's think about trying to, calculate that difference quotient. Well, let's not get ahead of ourselves. Here's one big problem. If I give you a point z0 in the set D, how do you know that the line segment from z0 to some other point z is contained in D? Is that line segment going to be contained in D for all points z in D? So here's a set D, here's a point z0, here's a point z, and look at the line segment from z0 to z. You have that densely dotted portion. This line segment from z0 to z does not lie in D for this particular value of z. So it doesn't make sense then to try to integrate over that line segment because f doesn't have to be defined on the whole line segment. Okay, you might say maybe we shouldn't use line segments, but more general curves. After all, we know how to integrate over all sorts of curves in the complex plane where the curves don't have to be straight lines. Well, suppose your domain looks like these two triangles at the bottom of the screen. Say z0 is the point in the triangle on the left, and z is a point in the triangle on the right. Well then, how can we connect z0 and z by a curve? If I do try to connect z0 and z by a curve, that curve is going to leave the triangle on the left, go out into the netherworld, and then come back into the triangle on the right. So there's no curve that's contained in these two triangles that connects z0 to z. So even trying to define this purported antiderivative over more arbitrary curves connecting z0 to z doesn't have to work because it's not guaranteed that the curve would live in your space D all the time. Okay, let's suppose we're even in the best case scenario. We have a set D contained in the complex plane, and there's a point z0 in D, such that for all other points z in D, there is a curve gamma z whose image lies in D, and whose initial point is z0, and whose terminal point is z. Suppose that I'm working on a nicely defined domain D, such that the pathological situations of the previous slides don't happen. Then certainly, because gamma z has its image lying in all of D, the integral over gamma z of f is defined. You don't have to worry about this integral not existing. And then we'd like the function big F of z, which we define to be the integral over gamma z of f, to satisfy big F prime of z equals little f of z. That seems to be the best analogy we can make with the fundamental theorem of calculus from real variable calculus. But here's yet another problem. What if we have another curve phi z, whose image lies in D, with initial point z0 and terminal point z, and we have the integral over gamma z of f not equal to the integral over phi z of f? I mean, why should these two integrals, 1 over gamma z, 1 over phi z, be equal? Just because gamma z and phi z have the initial point z0, and gamma z and phi z have the terminal point z, doesn't mean these two integrals should be equal. Would then the antiderivative depend on whether we picked gamma z or phi z? How would we know which one to choose if we have a multitude of paths to choose from? So to get around these issues, can the integral exist? Is the antiderivative well defined? We need to work on a slightly more precise set D that has a few nicer topological properties. So let's remember something. Fix a point z0 in the complex plane and a number r greater than 0. The open ball of radius r centered at z0 is the set B of z0r, which is all points z in the complex plane, such that the modulus of z minus z0 is less than r. In other words, it's sort of an open disk. And now we'll say that a set D contained in the complex plane is open if for every point z in D, there is a positive number r such that the ball centered at z of radius r is contained in D. So here's my set. It's open because I've drawn its perimeter with dashed lines. Here's a point in this set. Here's a ball centered at that point that's contained in the bigger set. Another point, another ball, another point, another ball, another point, another ball. This set D is open. And we'll say that D is path connected if for every pair of points z1 and z2 in D, there is a curve gamma whose image lies in D, and whose initial point is z1, and whose terminal point is z2. So here's my set D again. Here's a point z1, here's a point z2, and whoop, here is a curve from z1 to z2. There are many curves I could possibly draw from z1 to z2. And we'll say that a domain is a set D contained in the complex plane that is both open and path connected. So we can always fit small enough balls in this plane, and we can always draw curves between pairs of points in this domain. And for some counterexamples, say we look at the set of all complex numbers whose real part is greater than or equal to 0. This set is not a domain because it is not open. So say I take a point on the imaginary axis and I draw any ball centered at that point. Well, no matter how big or how small I make the radius of that ball, I'm always going to hit points in the left half plane whose real part is negative. So this set is not a domain, it is not open. Look at the union of the two balls here. I have the ball centered at -2 of radius 1, and the ball centered at +2 of radius 1. These balls are open, so their union is open, but this union is not a domain because it's not path connected. Say I start out with a point in the ball centered at -2, and I have another point in the ball centered at +2. No matter what path I might try to draw connecting those 2 points, I'm going to have to leave one ball, go out into the rest of the complex plane before I can go back into the other ball. So this set is not path connected. And at some mildly technical levels, we're going to see just how important and powerful being both open and path connected can be for a subset of the complex plane.